All right, what I want to do is I want to start by talking about functions. Functions, although this is an idea that you've undoubtedly seen before, functions are going to be a pretty important idea for us, specifically in Chapter 6. Chapter 6 is the chapter about linear transformations, and a transformation is really a function. So I want to just kind of pause for a second. Functions are something that we take for granted much of the time. And what I want to do is I want to just kind of zoom in and kind of look exactly about what a function is doing. And when I say a function, what I really mean is this is a rule. And this is a rule that's going to assign each element in a set D, okay, in a set D, to some element in some other set, say E. So what we're going to do is we're going to have some starting set, let's call it D, and then we're going to have some other set which we called E. Okay, and so we're just going to take each point in D and we're going to map it to some other point, some point in E. Okay, and maybe D and E are the same set. We're not really saying anything too restrictive here. Just D and E are both sets, and we're just mapping each element to D. We're mapping every element to D in D. Sorry, we're mapping every element in D to some element in E. And maybe there's two different elements, two different points in D that get mapped to that same point in E. That's okay. All we need is that every value in D has to go somewhere in E. Okay, that's really the only restriction. That's what a function is. You've seen functions, so the first functions that you've seen are functions where the set D and E are both, say, the real numbers. And then you talk about functions like f of x equals x squared. So before we get there, actually, the reason I chose D is that D is actually the domain. E is not the range, but rather the codomain. I'll explain what the range is in a few minutes. So this is the domain and the codomain. And so what we do is we write this notation that f is a function, and f is going to map this set D to the set E. If these two values are, say, x, and let me actually even just avoid x's and y's because we have some preconceived ideas there. But if this is, say, a and b, and this is the point C, then what we would say is that we would write this in the usual way. F of A is C, and F of B is C. Okay, so we would say both of those things. So both of those things are true. So F of A is B, F of A is C, and F of B is C. Let's just look at one of those pairs now. So in mapping A to C, we say that C is the image of A under F. Okay, so after applying our function F, and equivalently we say that A is what's called the pre-image of C, again, under our function F. Okay, so that's the big ideas for now. So we have, so we've talked so far about functions, domain, codomain, image, pre-image. Okay, that's the basic setup. And so you can think of just a generic function which maps real numbers to real numbers, where, say, f of x is, whatever, 4x plus 3. And what we want to do is we want to talk about different properties of these functions. And so if we were to take just some example, if I were to take 2 and plug this into the function, we would get 4 times 2 plus 3. That's 11. So this is saying that under this function f, so f is our rule, it's kind of this assignment, we're going to take each value x and we're going to assign it to this output 4x plus 3. I often, I should just say this, I often think of the domain as the set of all the inputs, and then our codomain is the set of all the outputs. Okay, that's just kind of generically how I think about those. And so if we plug in 2, so if we input 2, we output 11. So 2 is our image. 2 is the image, 11 is the image. 2 is the pre-image. Okay, so that is our, so 2 is the pre-image. So that's a function. And there's lots of different things that we can say about functions. If I have a function f going from r to r, where say f of x is x squared, then we know how this is going to work. We know that f of 3 is 9. We also know that f of 3 is 9, which is a silly thing to say after I've already said f of 3 is 9. But the point is that no matter how many times I plug 3 into this function, I get 9. That's what makes it a function. That's the uniqueness that we're talking about. Our outputs are exactly one value over and over. So if we plug in 3 to this function, doesn't matter how many times we plug it in, we'll always get 9. Okay, that's always our output. That's the property that makes this a function. It doesn't matter that there's another value that we can plug in to get 9. That part doesn't matter. The uniqueness that we're talking about is that every time we plug in a value into this function, we get out the same output. Consistently, we get 9 whenever we plug in 3. Okay, so that's a function. And what we're going to do is, there's a lot that we could say about functions. There's a lot that's going to happen here. But what I want to do is I want to really think about functions in the context that's going to be important for us. And that context is going to be in what are called vector transformations. A transformation is just a fancy word for a function. It's really nothing more than that. But a vector transformation is just going to be a function. I'm going to call it t for transformation. And it's a vector transformation because a vector transformation is going to be a function from some vector space V to another vector space W. So we have to understand vector spaces before we talk about vector transformations. But other than this, it's the same. So this is really the same setup as before. V is our domain. So our inputs are going to be vectors in V. Our outputs are going to be vectors in W. Okay, so a vector transformation is simply a function where the inputs and the outputs are vectors. Okay, other than that, it's exactly the same thing as a function. It literally is the same thing as a function. So that's a vector transformation. So for example, we could have t going from R2 to R3, where our rule is that if our input, I'm just going to, for convenience, think of R2 and R3 as column vectors. If our input is xy, then maybe our output is going to be, say, x squared, x plus y, 4y minus 1. Okay, that would be a valid vector transformation from R2 to R3. Your input is 2 values, your output is 3 values. We can say exactly the same stuff as before if we were to look at t of 2, 1. So if we were to let x be 2 and y be 1, then our outputs would be 2 squared is 4, 2 plus 1 is 3, and 4 times 1 minus 1 is also 3. So there we go. So our image is this vector 4, 3, 3. Our pre-image is that vector 2, 1. Everything is exactly the same. That's what a vector transformation is.